Hey guys, so this is a quick review on the unit entirely, and specifically we're starting with 1.6 Unit 1 review. This is in your packet. So the first question says, every morning at summer camp, one of the campers has to raise the camp flag to the top of the flagpole. For each graph below, describe the action of the flag raiser that might have led to this graph that shows the height of the flag as a function of time. So the way I would recommend that you approach this question and these graphs is by thinking about what's going on. Ask yourself what's happening as time goes by. So for instance, for graph, the first graph A, as time goes by, what's happening to the height of the flag? Now we know this is a line, and we know this is a linear motion. And we also know that a linear motion is associated with a constant rate of change, rise over run. So we can safely say for option A that what? As time goes by, the flag raiser raises the flag at a what? At a constant, how do we say height? Here it's not a speed, right? It's not distance. It kind of is a distance, the height per time. So we can say at a constant speed or rate. Okay. You can put at a constant height rate. Okay, that means maybe the flag raiser raises the flag 3 inches every 1 minute or every 1 hour, right? And he or she keeps doing that over and over again. That means every, 3 inches here that correspond to maybe 1. And then you keep going this way, 3 to 1, 3 to 1, 3, and so on, right? I mean, it depends on the scale, but the idea is there's a constant rate of change, and basically there's a constant change of the height of the flag as time goes by. So that's what this flag raiser is doing. This could be a potential scenario. For part B, notice that there is a sharp start, a sharp raise at the beginning, and then it flattens out. So that means we started quickly, real quickly, what we call pretty much exponential kind of raise, and then we flatten out, we slow down. There's no change. Notice here, this is the height, right? The height is not changing here. It's when it goes to flat, the height, that means the height is the same, which means the height is not changing. So what could have happened here? And you can, again, you can write the scenario that you want, but we can say the flag raiser raises or starts by raising the flag at we can say exponentially, right? At a fast rate. And as time goes by, he or she basically slows the process down or slows down. We can see at one point the height remains the same as time goes by. And this is the flat part of the graph. Now be careful, in this context, the flat means height is the same. Okay, which means the height has not changed. Flat part of the graph. There you go. So that's part B. Okay, so make sure you remember these items. Parts C and D, to move up a little bit. me see if I can keep them. I believe I can. Yeah, I can. So this is for A and B. For C, what's happening with C? C exhibits kind of like a miniature B, really, but repeated. If you look at C, this part of C looks very much like this, but it's a miniature, and then there's more of it, right? It's duplicated. So you can say that really C is a repeated motion of B, but what? But for shorter intervals of time, right? For shorter intervals of time. So you can say here, the flag raiser repeats similar behavior that was applied for graph B on shorter intervals of time. So basically, start fast, slow down, stop, raising the flag here when we say stop, right? Repeat. You see, the difference between C and B did not repeat. You just went fast, slowed down, and kind of stopped. For C, went fast, slowed down, stopped, then went fast, slowed down, stopped, and so on, and it did it 1, 2, 3, 4, 5 times. So that's C. For D is pretty much the other way around as B. It's not B, it's the other. We started slow. The flag raiser started raising the flag or change. Basically, when you raise the flag, that means the height of the flag is changing, right? The flag slowly, he or she then increased increased the speed or increased that height exponentially as time went by. Okay, so these are good descriptions of what's going on with A through D. Then is any situation more realistic than another? Why or why not? So which situation is more or less realistic? So could it be realistically that you're raising the flag exactly at the same time? I mean, perfectly at a constant rate? It is possible, and you get to a certain height and then you stop. So A is possible. B would look probably weird that you're raising the flag very fast and then you're stopping at the end. It's possible. C, you're raising the flag fast, stopping, raising the flag is like not very traditional. And D, you start slow and then you quickly raise the flag. So I would say if we're going with something, kind of like a steady rate, A could be a good option, right? A could be a good option. So, I mean, I don't know, maybe B would look like they start. I mean, anything that has a stop at the end could possibly be, but think about what's happening with a flag raiser. So, have you ever seen someone raise the flag super quickly and then stop? Or someone start very slow and then pick up, right? Or someone repeatedly doing fast, slow, stop, fast, they're not very, these are not very common. So I would say A looks like a safe option. Option A or choice A sounds more, and you always want to make sure your answer sounds mathematically correct, right? Sounds more realistic then the other options, as it shows that the flag was raised at a constant speed, right? Now, basically, you start from 0, and then you can do, if you have some sort of regimented motion, right? You can do also not very easy, but a constant speed. If you have additional options, or if you feel like other options may be good, then please feel free to share them in class. Now, again, some may say it's difficult to maintain the same exact speed as we go by, right? Like keep going at 3 something per second. It's tough. So A is also tough. I would say maybe B is also possible. Maybe even I'm thinking now that I'm thinking about it, B is a better option because you start raising the flag faster and then you kind of slow down once the flag gets closer to B. Sounds reasonable. As the flag raiser starts fast and as the flag reaches the top, the raiser stops. So that's possible. I'm kind of maybe liking it now even better than this option. So because it's difficult to maintain a certain speed, like 3 meters per second, very difficult, super difficult to kind of maintain that as a human. I mean, unless there's a robot who's doing that, right? So yeah. I'm trying to get rid of this option, but it's not letting me. Okay, no problem. No problem. So let's clear it up. Number 2, the amount of water in Maria's rain barrel is represented on the graph. Is each of the following a possible interpretation of the graph? Circle your answer. So let's see what we have here. We have the barrel started off empty. Yes. This is time on the x-axis and the water in gallons on the y-axis. This is where the barrel starts empty at 0. There's 0 gallons at the start at time equal to 0. So that's a yes. Maria's used water. Maria used water from the barrel to water plants after 35 hours. So this is the 35th hours, 35th, right? If she waters, that means whatever was in the barrel is going to go down in terms of capacity, or not capacity, but the amount of water, right, in gallons. So that is also a possibility. C, it rained for the first 10 hours. This is the first 10 hours. So what's happening in the barrels? We're gaining water. So that is also a possibility. Okay, so all these 3 are possibilities. Now moving on to number 3, the question says, Varian drove to work this morning. It took him a total of 15 minutes. He stopped at a traffic light for 3 minutes after driving for 5 minutes. Sketch a graph to represent the distance from Varian's house during his drive to work. So he drove to work this morning. It took him a total of 15 minutes. So let's say this is 15 minutes here, 15-minute mark. Let's go maybe 5, 10, 15, something like that. Okay, so he drove a total of 15. He stopped at a traffic light for 3 minutes after driving 5 minutes. So he drove. Now, we don't know how he drove. We don't know if he drove at a constant speed, but I'm going to assume that he drove at a constant speed up to the 5-minute mark, right? Somewhere right here, a little bit more. And can erase this part here underneath it. Oops. So we can go, this is up to 5. And then he stopped at traffic lights. So remember, he stopped at a traffic light for 3 minutes after driving 5. So the first thing that I modeled here is the first 5 And we can do 6, 7, 8. Maybe 6, 7, 8, 9, 10. So this would be the 8th mark here, the 8th minute. So he drove, and 3 minutes he stopped for 3 minutes. So this should map down to 8, okay? And then what happened? Sketch a graph to represent. He stopped at a traffic light. That's it. It's about 15 minutes after driving, 5 minutes. Sketch a graph to represent the distance from where it's home during. Do we know any more information? We don't know any more. We don't have any more information. So this is a stop at traffic light, and then we can do whatever we want here, right? But if we're taking the distance, you have to be careful. If the context of the distance is distance from home, then as he goes to work, the distance from home increases, right? If this just distance driving, so it's probably going to be something like this. He stopped, that means, remember, he stopped, that means the distance has not changed, right? That's why it's flat here. And then you're going to go up. It doesn't have to be at constant speed, but you know, we're assuming he's driving at a same rate, 30 miles an hour, 24 miles an hour. So it could be something like this. Okay, and lastly on this page, number 4, mapping. Mapping diagrams, basically. Make a mapping diagram for each relation, determine if the relation is a function, and explain why it is or is not a function. So basically, remember, when you start mapping, think of the first or the leftmost diagram, which is here. It's the x and this is the y. So in your mind, think about the smallest values, which are -3. Now, you do have to put them in order. You don't, but it's nice to put them in order. -3, -1, 0, 4, and 5. Again, you don't have to, okay? But -3, but be careful, because -3 maps to -9, and -1 maps to 3, 0 maps to 0, 4 maps to -9, and 5 maps to 6. And make sure, definitely, you need to put the arrows. You definitely have to do that. Now, here's the thing. I wrote -9 twice, and I know 4 is going to map to that. So should I write it twice? Should I write the values twice in the mapping diagrams? The answer to that is no. So I can initially write it, and then when I see that, oh, it's repeated, I can cross it out and erase it, and then say what? 4 also maps to -9, and erase it from here, and then make the 5 map to 6. Okay, now the question was, is it a function? Remember, we can have 2 values from x. We can have 2 values from here map to 1 value from here. That's okay. So that is okay. So this is, yes, this is a function, because for each x value or each input, there is at most or unique one y value. Okay, so that means from each point in the x diagram, mapping diagram, there's only 1 arrow coming out of it. If there are 2 arrows coming out of it, then it's not a function. And then we can try b here, same idea real quick. 0. I'm just going to put them not in order. It's fine. Either way is fine. -2, 2. 5, 0. -2, -2. Just be careful. So again, I don't want to write -2 twice in the x value, so I write it once, and then 3, 4. So 0, 5, -2, 2, 5, 0, -2, also a -2, and that's the bad thing here. You have one x value, -2, namely mapping to both 2 and -2. That's not good. So this is not a function. You can see here, no, this is not a function. The x value, -2, or the input -2, maps to 2 different, remember, it's about different or unique, right? different y values. If you say two y values, that's not really accurate. It's two different y values. And you can put, to be specific, you can put 2 and -2. And that's pretty much it. Okay, so this concludes this review for these 2 pages. And I'll see you in the next video.